Hi guys, in this next question we're taking a look at writing exponential functions from a graph. We've seen a little bit of it from a table, but now we're given the graph of an exponential J-shape curve and we want to come up with the function rule, the equation. So in this case it says write the function f of x. So I want to make sure when I'm done it should say f of x equals. For the exponential function, explain how you determined your equation. So I'm going to go over a few options that we can do here. Option one would be an algebraic approach. The first thing I would say is knowing the general rule of an exponential function, which is this. Okay, for some function f of x, it's equal to a times b to the x power, where a represents the initial value, very similar to growth and decay. You see how this is related. And what do we call initial values with graphs? What do we call starting points? Generally, this is our y-intercept, or where x equals 0. And b, we can call our, there's a few different words. You can call this common factor, common ratio. In other words, what are you multiplying by each time? What is the pattern? Times what? Times 3, times 2, times 1/2, something like that. And x is our variable. X is our exponent, which plugging in different things will give us different results. So some other basics really quick, just in general terms. We have two different types of exponential graphs. We have something like this, which is called an increasing function, and then we have a decreasing function, which looks like it's flipped over, the y-axis. So what's the difference between these? It all relates to the base, b. What we said, that the pattern, what you're multiplying by. If b is anything greater than 1, it will be an increasing function. If b is anything less than 1, it will be a decreasing function, be getting smaller and smaller. This has to do with basic exponent concepts. If you have something like 1/2 and you're raising it to a higher power, it's going to get smaller. You'll have like 1/2, 1/4 if you're raising it to the second power, let's say. Whereas with anything bigger than 1, obviously it gets larger as we make that a bigger exponent. So we want to keep that in mind. And just by looking, we should note that RB is probably going to be the left case here since we have an increasing function. That's obviously useful to know. If you write the equation rule and then you realize, like, oh man, I have a fraction in there, and you look at your graph and you see an increasing function, obviously something's off. And it doesn't hurt to know it either. So let's start. When you're doing these, some things that I would make a note of, you want to use nice or good points, if you want to call them that. It's not a technical term, so I'm putting it in parentheses. What do I mean by nice points? I'll give you an example of what they're not. This would not be a nice point right here, right? I would be guessing if at whatever the y value is there. I have no idea what that is. Maybe it's a half, maybe it's a quarter. Nice points are points that actually hit a specific point on the graph that you can clearly see. They hit a corner. If we want to think of those as little squares, they hit a corner somewhere that I could definitively say, hey, this is the point. This is where it is. I'm not guessing. So some nice points that I see, luckily the y-axis is nice. This point looks pretty good. This one, there's a few nice ones. It's a pretty nice graph we have here. So now that we have those few points, those few nice points identified, we're going to try to look for a pattern, something we notice that's happening maybe. One thing we got lucky with here, and we're going to take a look at another example in a second where we don't see this. Luckily, the y-intercept was one of those nice points. So right away, I know the a value, or the y-intercept, which is 3. And that was right here. It clearly passed through 3. Sometimes they make these harder by making them not pass through that point. So we'll take a look at what happens when we see something like that in a second. Now the pattern here, I notice, I'm going to write them down just so we could see it a little bit differently. When x is 0, we have 3. When x is 1, we have 6. And when x is 2, we have 12. Okay, I'm just writing down the coordinates, almost like a little table. Okay, so what's the pattern? Now that we see it this way, it's pretty clear that in each case we're doubling. Okay, we're going times 2 each time. So this would make our b value, our base, 2. Now I have everything I need to write the actual function rule, so I'm going to do that. Remember, one thing you do not want to do is this. That would be a huge mistake, a huge conceptual error that, hey, I can multiply things that have exponents attached to them. Obviously, we cannot do that. I don't even want to leave it on the page just to confuse anyone. So that would be your final answer. Putting the 2 in parentheses, if that helps you separate it, that's fine. But 3 times 2 to the x power. Another option, I unfortunately don't have my calculator, on a graphing calculator on my iPad, but on your TI-84, I'll write down the buttons. You can hit Stat. So this is a different strategy that I mentioned earlier. You would hit Stat, select Edit, and under list 1, you would type in the x values of those points. Under list 2, you would type in the y values of those nice points. You actually only need 2 of them. So you could do something like this. You do 0, 1, and 3, 6. Typing in the third one won't hurt, but it's just not needed. So you would type those in, then you would hit Stat Calc. So hit the Stat button again, but now you're going onto Calc. Make sure that these correspond as well. And you're going to select 0. Just hit the 0 button, or you could scroll down. It'll say Exreg, which is exponential regression. And it will literally spit out that same formula for you. It even gives you the format up here, the a times b to the x, to remind you what it should look like. So that's a calculator option. And obviously all the work we've shown here, and even if you did the calculator strategy, this would be our explanation. We don't have to write a formal essay on what we've done, but we could just say something along the lines of, I used the table feature on my graphing calculator and I did exponential regression, and this is the equation I got. Or the algebraic approach, we could say, I found the y-intercept and I found the common base, the common ratio, to be 2. And all of our work is justifying that. So we've explained kind of how we came up with it. Okay, I also made note, I did call it f of x. That's something we want to focus on using proper terminology, not to lose a silly half a point or a point along some way. Okay, so quickly, let's take a look at that other case. And you see what in this case, we're looking at g of x. So I'm going to write down that same definition. But this is what I was mentioning earlier. Now we don't have a y-intercept. Okay, there is a y-intercept physically, but we don't have one that I could clearly see. It's not a quote-unquote nice point. So I'm going to highlight the nice points. I think I only actually see 2 of them. Okay, 2 nice points over there, and everything is fractional on the other side. Nothing even that I could make like a quarter or a half or something like that. So not a problem. Exponential functions are actually defined by just 2 points. So I'm going to write them down. We have -2, 6, and -1, 3. Okay. So in this case, we don't have a y-intercept. That would be where x equals 0. So I can add that. We can pick out a pattern. Luckily, these are right next to each other, -2 and -1. So I'm not skipping anything. There's no jumps, like we say. I could just strictly say, hey, what did I have to do to go from 6 to 3? In this case, we always want to think in terms of multiplication. You don't want to say division. This would be multiplying by a half. So I already found b relatively easily. Now I'm going to continue this one step further. You might say, what's the point of that? By having a point that starts with 0 and having the y value that goes with it, what did I just find? What does this point represent? This is the y-intercept. Okay? You could do it in this coordinate way. You could write it however you want. You can make a table and do this pattern, whatever works for you. But I've just found the 2 things that I need here. I found the common base, the pattern, times 1/2, times 1/2. And I found the starting value, the y-intercept, or where x equals 0. Sometimes this might be off a little bit. Maybe we have to go 2 or 3 jumps. But in this case, we just had to do 1. It also kind of makes sense. 3.5 is 1.5. And if we look closely, that looks right around, kind of makes sense. I wouldn't want to say that just by looking at the graph, but now that we see it's actually 1.5, it does make logical sense. Also, what we mentioned earlier, once we put our function together here, let's look at the base that we get. So 3/2 or 1.5 works. and the common multiplier is 1/2 to the x power. We mentioned earlier, if the base is less than 1, it should be a decreasing function, which this is. So everything works out, everything passes all our little mental tests that we check everything with, and that's g of x. So this is writing the equation of an exponential function. Hopefully this helped. Thanks for watching.